Okay, this is college algebra. Review section 1. There are 4 objectives in this section. The first one is to work with sets. The second one, classify numbers. Third one, evaluate numeric expressions. And the fourth one, work with properties of the real numbers. So, go to the next page and do number 1, work with sets. First of all, what is a set? A set is a well-defined collection of distinct objects. Let me write that one down at least. A set is a well-defined collection of distinct objects. Okay, what are the objects called? The objects are also called elements. And what does this well-defined mean? Well, if you're given an object or an element, then you will be able to easily determine whether it belongs to the set or not. What is an empty set? That's a set that contains nothing, no elements. It can be written 2 different ways: braces that have nothing in it, or a 0 with a slash through it. Now I want to make sure you understand that it is not the same as a set of braces with this 0 and slash. This in fact is not the empty set. This is a set that contains the empty set, which is something. And so even though this empty set has nothing in it, this other set contains something. So don't mix the two. It's either braces with nothing in it or that 0 with a slash through it. Okay, there are different types of notations. There is roster notation. That is when you just use braces and list whatever you have, usually numbers for mathematics. Put them in these braces. You list your elements. It is a roster. The other one right now is set builder notation. Now, set builder notation uses the braces also, but the first thing you put is sort of a picture or a, I guess, a representation of that element. So this is what the element looks like. Then you use a vertical line. You can use a colon also, but I prefer the vertical line. This means such that. And then there's some rule on how you choose all those elements. So, and end it with a brace. So it'd be something like an X is used an awful lot, but we're going to look at some others. This is the set of all X such that, and perhaps you just want to say X is greater than 0. Now, if you don't put what set you're pulling that from, we'll assume it's the real numbers. So this is really saying X is a real number and it's greater than 0. This is set builder. You could build the set if you needed to using that rule. But it's so big usually that you can't list them all. If it's small enough, then you can use roster notation for 1, 2, 3, 4 things, just so it's not too big. You can list them in roster notation. Now, you never repeat elements. Perhaps for some equations and things, you would have 2 that comes up a couple times maybe, but you'd only have to list it once. Okay, when are sets equal? Well, let's see. If I have a set A, which is the set containing 1, 2, 3, and 4, and I have a set B, which is the set containing 1, 2, 3, these two sets are not equal. If I have another set containing 1, 2, 3, we know that B is equal to C. They are exactly the same. But you can also talk about smaller sets. We know that B is a subset of A. This is sort of like less than. You can put the or equal to sign here, so these could be equal. Perhaps B is smaller, but it could be equal. And our book, I think, doesn't distinguish between the two. We also know that C is a subset of A, but B and C are equal. And I think our book is always going to put that line underneath it. So that's how you do subsets and equal sets. What is the intersection of two sets? Suppose I have A, this is intersect B, the intersection. Those are all the elements that are the same in both sets have them. So both sets have a 1. Both sets have a 2. And both sets have a 3. But both sets don't have a 4 or anything else. What about the union of two sets? Well, that's when you put two sets together, you get, let's do it down here, A union B. It's sort of like a U without that extra leg. So that means you list everybody, but you don't have to list them more than once. So A has a 1, a 2, a 3, and a 4. And B has a 1, a 2, a 3, and they're already listed. So the union of those two sets is just this. You don't have to list 1, 2, and 3 twice. The union and the intersection of two sets. There's also something called the universal set, and it uses this really fancy U. Now, it doesn't have to be the universe, but that's in a sense what you could use. It has to be a big enough set to include all the things you're interested in. In our case, I guess we're just interested in everything up through 4. But perhaps we said, no, we want the universal set to be 1, 2, 3, 4, and 5, for whatever reason. Then you can talk about the complement of a set. The complement of A, which is A with a bar over the top, is all those things in the universal set, but not in A. So A has 1, 2, 3, 4, but the set consisting of 5 is the complement of A because 5 is in the universal set, but it's not in A. The complement of B, or C, since they're equal, is 4 and 5. Now I keep putting these in order. It's sort of just, I guess, what you might want to do, but you don't have to. The order is not important for these things. And that's what braces usually mean in mathematics. Order is not important. Parentheses is when you want order to be important. Now you can also do these with Venn diagrams. Oh my gosh, I got this too big. Let me start this over again with the right size brush. Okay. So Venn diagrams, named after a guy named Venn. They set up pictures. It's nice to have the pictures you can see. This is the universal set. And let's say it's 1, 2, 3, 4, 5, and 6. We'll say that set A is 1, 4, and 5. Set B is set 3 and 6. And set C we'll say is 1, 2, and 3. So, what is A union B? Well, That's A and B together. That's 1, 4, 5, 3, 6. Doesn't have to be in order. What is A intersect C? Well, that's what they have in common. You can see just the 1 is where A and C have that in common. So Venn diagrams are a nice picture. What is the complement of A? That's all that stuff in the universal set that's not an A, so that's 2, 3, 6. And we can do all sorts of combinations of these things. What are disjoint sets? Those are sets that have nothing in common. Up here, A and B have nothing in common. So A intersect B would be the empty set. They are disjoint sets. Okay, that is really first objective, working with sets. Let's pick another color here, and then let's do classifying numbers. So this is objective 2, classify numbers. And the way to do that is our sets. Suppose I have a set here. It's 1, 2, 3, 4, 5, 6, 7. The counting numbers, we also call these the natural numbers. And the symbol for that is a double strike N for the natural numbers. When you add just one more element to that, include the 1, 2, 3, but I'll now add a 0, we have what we call the set of whole numbers. And at one time they thought that's all they needed there. But then they said, well, hold, suppose I borrow something. So I need the opposites of those ones, negative 1, negative 2, negative 3, and then you go to that negative infinity. And with those and the 0 and the 1, 2, and the 3, I have all the integers. They make this, I think it's supposed to be an I, but it looks to me like a Z. So if you're French, you would say it's Z integers. Then you have all the fractions like 1/2 and 7/16 and stuff like that. All those fractions, put those together with the integers, which includes the whole numbers, which includes the natural numbers, and you get the rational numbers, and we use a double strike Q for that. Now a separate set, not part of the rationals, but really just as big. These crazy numbers, the square root of 2, pi is in here, Euler's number, 3.718281828. Or is it 2.7? 2.718281828. There's this delta, which is Feigenbaum's constant. All these crazy square roots, square root of 3. Those are irrational numbers, and you use a Q, but then you put a little single quote for Q prime. So the rationals and the irrationals together make up the set that we sort of call the default for all this stuff. The real numbers, and finally a double strike R, which makes a whole lot of sense. Now this is where the set builder notation can be sort of nice. Rational numbers can be written several different ways. One way is every rational number will look like a fraction. This fraction, then we can use anything we'd like, but usually I guess for mathematicians we use A over B. The set of all A over B such that, where do we choose A and B from? A, B are elements of the integers. So, 1 and 2 are integers. 1 over 2 is a rational number. 7 over 16 integers. Even the number 1, which is really 1 over 1, is this quotient of integers here. Another way to do the rational numbers is the set of all numbers whose decimal and this decimal either repeats or terminates. It repeats. So, things like 0.3333 repeating, which is really 1/3, two different ways of writing a rational number. Anything you can do like that. If you can do 1 point and then a bunch of sixes, then this is 1 2/3, which is really 3 times 1 plus 2, or 5/3. And there's your quotient of two integers. A repeating decimal. If it's a terminating decimal, things like 2.5, which is 2 1/2, which is 5/2. So if it repeats or terminates, it is a rational number. This is sort of the neatest way to write rational numbers. Now, when you're doing some of these things, because that terminating and repeating stuff, the square root of 2 is exact. So if I ask for an exact answer, and you come up with a square root of 2, write it as the square root of 2. 1.414 is approximate. Your calculator will give you more places, but the square root of 2 is not equal to, it is approximately 1.414. So you'll be asked at times to round this to a certain number of decimal places or truncate it. This is rounding and truncating, could be the same. Let's see, the pi is exact. So if you want exact and it comes out to be pi, use pi. Or the approximation 3.1415. Well, the next digit would be a 9, and then this thing goes on and doesn't repeat or terminate. So you know there's no way to write it exactly as a decimal. But if you wanted this to be rounded to 4 decimal places, it's 3.1416. If you want it to be truncated, see, this is rounded. When you truncate, it would just be 3.1415. You don't care about the 9. If you want it truncated to 4 places, you just slice off the rest of it. Okay, that is objective 2. Objective 3, a deep blue. This is evaluate numerical expressions. And this is where your order of operations comes into effect. So if you remember, please excuse my dear Aunt Sally. It's not so bad. That's pretty good to remember. The P stands for powers. Parentheses. The E is exponents. The M is multiplication and also division for the D. This goes left to right. So these are sort of the same level. Multiplication, division, whoever's left of this is done first. And then the A for add and S for subtract. That is also same level, left to right. It might be interesting, that doesn't sort of tell you what to do. Suppose you have a -2 squared. What is your answer? Well, you do the exponentiation first and then you apply this negative. So it's a negative 4. If you wanted it to be a positive 4, you'd have to include that negative 2 in parentheses, so it would square the negative 2. That exponent works with just the nearest thing. Then you get the positive 4. So be a little careful. We're going to work out a problem, and I think this may be all you need for this. Suppose you have 2 plus 4 plus these square brackets, or another grouping symbol, times the parentheses, 10 minus 6, close parentheses, close the square bracket, and suppose you wanted to do this step by step. So let's see, we do the innermost parentheses first, or grouping symbol. So 10 minus 6 is 4. Then the innermost here is the square brackets, but multiplication has precedence over addition. So 2 plus 4 plus 2 times 4 is 8. And then you do these parentheses. 2 plus 8 and 4 is 12. And 2 plus 12 is 14. So make sure you use the order of operations. Sometimes it doesn't matter. When we were at this point right here, we could have forgotten about this because it doesn't matter. The grouping, we'll look at that later too, for the properties of real numbers. So that's objective 3. Objective 4. So this is the last objective, objective 4. But it's got the most information, and this is really good quiz material right here. So keep that in mind. These are properties of the real numbers. I'm going to use that symbol. And there's a lot of these things, but I think most of these you probably know. You've not maybe thought about them that much. We want you to think about them a little bit more. What is the reflexive property? What is the symmetric property? What is the transitive property? What is substitution property? Now this list are the properties of equality, because this shows you that things remain equal, if you do these things to them, I guess. The reflexive property is like looking in a mirror. You see yourself, A equals A. And you might wonder why that's important. In mathematics, you have to develop all your stuff from the ground up, and this is where you can start equations. You know, because of the reflexive property, you don't have to prove this, A equals A. And then you can work from there. The symmetric property is if A equals B, then you can turn it around. Symmetric means you flip over the other way. B equals A. The transitive property means you can get this transfer to go to another one, I guess, in a sense. If A equals B and then B equals C, well, you can skip the middleman and said A equals C. Transitive. You go past B. And substitution is sort of a crazy one. It's many times, if you did geometry, transitive and substitution were sort of almost the same thing, but there's a little difference here. If A equals B, then in an equation, B can be replaced. or substituted by A. You can also take A and substitute B, so it doesn't have to be B, it can also be A, and you substitute with B. So those are the properties of equality. There's some other ones that we might get to here. What is subtraction? Well, we never really subtract. A minus B is really A plus the opposite of B. What is a quotient? Well, we can say, I guess, that we never really divide. A divided by B is really multiplication. It's A times the reciprocal of B, provided B is not equal to 0, of course. Can't have 0 in the denominator. Can't divide by 0. So let's go to a new screen. The multiplication property of 0, is it just what you think it is? A times 0 is 0. A can be any real number for this stuff. The division property, and this is really the division property of 0, it's 0 divided by A is 0. And the division property of 1, A divided by A is 1. And in this case, this denominator still cannot be 0. What are the rules of multiplying and dividing? Like signs? When you multiply or divide and they have like signs, they are positive, right? And unlike signs, one is positive, one is negative, that product or quotient is negative. There's one called cancellation. Do this all the time. If we have AC and that equals BC, then you can essentially say, let's divide both sides by C, and you get A equals B. So you can cancel that C. You can do that with division too. It can be AC over BC, and the C's cancel, and you get A over B. Now in this case, make sure that B and C are not 0. The next one is one you'll use quite a bit when you're factoring. If A times B equals 0, then one of the following, either A is 0, or B is 0, or the both is 0. And now we get to something called the field properties of the real numbers. Anything can be a field. You need a set, so we're going to use the real numbers. You need two operations. We're going to use addition and multiplication as you know it. There is closure. There is the commutative property. The associative property. Identity. Inverse. And I got to squeeze this in. Distributive property. Now most of these are separated into the addition and multiplication part of that. So let's change colors and make this a little nicer. What is the closure property? Well, these sets are closed under addition. In other words, if A or B or C are elements of the reals, and you take A and add it to B, you still get an element of the reals. That set is closed. You'd never jump out of that set and get some crazy complex number. If you multiply A times B, you still get a number that's a real number. And you might say, well, that doesn't sound really important. Doesn't that always happen? Not always. And those things, those sets, then are not fields. The commutative property. If you add two things together, it doesn't matter. You can do A plus B or B plus A. If you multiply two things, you can do A times B or you can do B times A. It doesn't matter. The order for addition and multiplication doesn't matter. Commutative is order. Associative is grouping. A plus B plus C equals A plus B plus C. And what this says is I can add these first two together and then add the third one. Or I can add the second two together and then add the first one. I get the same thing. Same here with A times B times C equaling A times B times C. The identity. What's the additive identity? Well, it's the thing when you add to something, you get the exact or something back that's identical. You add 0. 0 is the additive identity. The multiplicative identity is when you multiply by something, you get that same something back. When you multiply by 1, I'm going to put these little lines underneath my 1s to make sure they don't look like L's or something else or some stray mark on the board. What is the inverse? Well, when you take a number and add something to it, you get the identity, 0. What do you add? The opposite of A. When you multiply by something, you get the identity, 1. What do you multiply by? 1 over, or the reciprocal. Now here A can't be 0, of course. And the distributive is what connects the two operations, addition and multiplication. A times B plus C, you can distribute the A over addition. You don't distribute addition over multiplication. It's multiplication over addition, AB plus AC. And those are the field properties for the real numbers. Now, what is the least common multiple of two numbers? It's the same as the least common denominator. If you're doing fractions, and that's why this becomes important. But if you take two numbers, say 6 and 8, and you start multiplying, 1 times 6 is 6, 1 times 8 is 8, 2 times 6 is 12, 2 times 8 is 16. Someplace along here, as we keep multiplying, we're going to get a common multiple. 3 times 6 is 18. 3 times 8 is 24. 4 times 6 is 24. Ooh, there it is. The least common multiple is 24. That's also if these were denominators, like 1/6 plus 1/8. When you add fractions or subtract fractions, you need a common denominator. So you'd have to multiply this by 4 to get 24, and this by 3. But if you do that to the denominator, you must also do it to the numerator, so that you're just multiplying by 1. And multiplying by 1, the identity doesn't change things. So you get 4 24ths, and you get 3 24ths. Once you've got a common denominator, you add the numerators. 7 24ths, leave the denominator alone. Now you can also reduce that, but if you use the least common multiple, least common denominator, most of the time, not always, you won't be able to reduce it anymore. What is the greatest common factor? Well, that's when you have to factor things. So if you use that 6 and 8 again, all the factors of 6 is 1 times 6, and 2 times 3, and when you reach the middle, so to speak, you're done. Here's 1 times 8, and then it's 2 times 4, but 3 doesn't work, and now you've made it to 4, so you've made it to the middle. So the greatest common factor, well, 1 is a common factor, but it always is. 2 is a common factor. Is that the greatest one? 3 is not common, 6 is not common, so 2 is the greatest common factor once you factor them. Does that make sense? Common multiple is when you're multiplying. Now, the rest of this will be examples from the assignment page. These examples come from section Review 1. I'm going to put an underline just to make sure that looks like a 1. You'll notice I do that. These examples from page 15. Your assignment has got to be all the odds, so I'm going to do some evens. First of all, the universal set is going to be 0 through 9. Set A, let's see, 1, 3, 4, 5, 9. Set B is 2, 4, 6, 7, 8. And set C, 1, 3, 4, 6. And if we look at number 10, which uses these sets, this also should show you how you can get at least 4 steps, because I'll be asking you to show 4 steps on all your stuff. And if you don't always show 4 steps, I can take off some points then, so don't let me do that. The first one looks at A union C, and you might say, how are you going to get 4 steps out of that? Well, right now we've got at least 1 or maybe 2 steps just writing these doggone sets. So one way you can then add to that, A is the set 1, 3, 4, 5, 9. Union C is the set 1, 3, 4, 6. For the union, we want to use all elements. So this is going to be the 1, the 3, the 4, the 5, the 9, and then, well, I already got 1. I've already got 3. I've already got 4. I just need the 6. And that's all the sets in both of those. So, this may look like 3 steps, but with this explanation up here, and sometimes you can say that I'm going to use this for problems, the same do number 12 and 20 also, I guess. This is for problems 10, 12, and 20. And that way you can get your steps for those two. Because I'm going to run out of room here, for 12 they want A intersect C. Well, you can write out A and you can write out C. We've already got that. But now when we do intersect, we want those that are in common. So you can write that intersect elements in common. And what I'm looking for with these steps, I think, to me it really makes sense, that if you write something down, you'll remember it better than if you just look at it. So writing these things down will make a difference, I believe. And if you write intersect elements in common, when you come back and look at this to review for the test, then you won't have to look it up in the book maybe. You'll say, here's my sets. I wanted A intersect C, all those in common. Let's see, for A and C, it's 1, it's 3, it's 4, but not 5 or 9 or 6, so that's it. And for number 20, we want the complement of B intersect the complement of C. Now, this is going to really squeeze this in here. But the complement of B, I'm going to put that up here. B complement is, B has 2, 4, 6, 7, 8, so I have to include the 0 and the 1, not the 2, but the 3, not the 4, but the 5, 6 is there, 7, 8, and the 9. That's B complement. How about C complement? Let's see, I need the 0, and I don't need the 1 or I do need the 2. The 3 is in C, the 4 is in C, and I need the 5. The 6 is in C, but 7, 8, and 9 are not. So, now we look at the intersection, those in common. See if I can squeeze these in. So, those in common for B, complement of B, complement of C are 0, 5, and 9. Is that right? 0, 5, and 9. Yep. So, with a little more work, you could get 4 steps on all these. Don't squeeze it in on your paper. It'll make it harder for me to grade, and you don't want it hard to grade. Then teachers like to take points off. Let's go to another problem, number 22. Let's change colors just because it's more fun to have different colors. Lovely shade of yellow. Number 22. We have this set. -5/3, 2.060606, and it keeps repeating that. 1.25, 0, 1, so 1, let me put a line underneath it, and the square root of 5. Okay, they want to know which of these are natural numbers. That's the symbol for natural numbers. It is the set. Natural numbers are the counting numbers. It's just the 1. Yeah. Which of these are whole numbers? Let's see, whole numbers includes the 0, so it's not just the 1, but the 0 and the 1. Which of these are integers? Z integers. That's just the 0 and the 1. Which of these are rational numbers? That's the Q. All these fractions, the negative 5/3. Now, if it's a decimal, it can be repeating. That's a rational number. 2.06 repeating. If it's a decimal, it can be terminating. So 1.25 is also rational. 0, because any integer is also a rational. So is 1, but square root of 5 is not. That's irrational. Which is the next set that they want to look at. Q prime is just this 1 square root of 5. Does this make sense? I hope. Number 36. They want 5/9, and they want rounded to 3 decimals. And they want truncated to 3 decimals. So first of all, what is 5/9 as a decimal? It's not a whole number, so it's 0 point. And if you do the long division, 9 divided by 5, here's the decimal. So go zeros times. So how about then, it's point. It's 5 divided by 9. Boy, did I do that wrong. 5 divided by 9 decimal. Okay, so 9, there's no 9s in it, but 50. Let's see, there's 54 times 6, so 45 must be 5, right? 5 times 9 is 45. So there's another 5. Bring down a 0. Oh, there's 50 again. Oh, so this is 5, 5, 5, 5, 5. So this is 0.5. I'm going to put 4 places and then repeating. Because if we want it rounded to 3 decimals, then we need 0.556. If the 4th place is 5 or above, you go to the next one. If we want it truncated, it's 0. Just chop off after 3. $42. Let's go to a new screen. Write using symbols. Just going to do the symbols right away, huh? The sum of 3 and y is the sum of 2 and 2. So, the sum of 3 and y is 3 plus y. Is, the verb is the equal sign. The sum of 2 and 2 is 2 plus 2. So, you've written that English into a mathematical expression, equation in this case. And number 62, the last one I think we'll do. 2 minus 5 times 4 minus 6 in these square brackets times 3 minus 4, close the square bracket. Okay, here's where you've got to use the order of operations. You do the innermost parenthesis first. So 2 minus 5 times 4 minus 6 times 3 minus 4 is a negative 1. Now we do these square brackets. 2 minus 5 times 4 minus. Well, 6 times a negative 1 is a negative 6. So 2 minus, this is, I'm going to do one more step here. 5 times 4 plus, because minus a negative is plus 6. So now this is 2 minus, well, I have to do multiplication first. So that's minus 20 plus 6. 2 minus 20 is a negative 18 plus 6. Negative 18, positive 6 is a negative 12. So, I believe we've gone through enough of these examples for section R1. You should be able to do the homework and get it to me as soon as you can so I can start grading them. We'll see you in R2 or D2.